Okay, so good afternoon, distinguished guests, college, friends, and also audience online. So I think there are about 20 participants online. Yes. So welcome to our SKLMP Distinguished Lecture Series. And today, our distinguished speaker is Professor Zhiguo Yuan, Chair Professor of Urban Water Management, Global STEM Professor from the School of Energy and Environment. So now may I welcome Professor Kenneth Dunn to give us the opening speech.
Thank you, Phoebe. The MC today is Dr. Phoebe Wen. She is our research assistant professor. So on behalf of the State Key Laboratory of Marine Pollution of City University of Hong Kong, I offer my warmest welcome to all of you. So the State Key Laboratory of Marine Pollution was established in 2010. So we focus on 3 research areas. The first one is on marine pollution monitoring and control technology. The second area is on eco-safety, about seafood safety and also water and sediment quality management. And then the final one is about when the pollutants being discharged into the marine environment, how the marine organisms and ecosystem respond to that. And if you clean up the water, and then how the ecosystem recovery. We also develop technology, how to accelerate, speed up the recovery process. So those are the 3 key areas we are interested. Then last year, we also start new areas into marine or ocean carbon neutrality, as well as support to the blue economy. Those are new areas. So today, we are really happy to have Professor Yuan with us. He's a newly appointed STEM professor at the School of Energy and Environment. So I'm really happy to have him to join CTU, and also he joined as a member of our State Key Lab. So if you're interested to work on those research area I mentioned, please feel free to talk to our student, our research staff, and also our teachers. So right now we have around 70 members from 8 local universities joining our State Key Lab. So if you want to find out more, please go to our website, read our newsletter, and also browse around our website. We have many sophisticated instrumentations. You can also use them if you work with us. So let's move on to introduce our distinguished speaker today. Professor Yuan is a chair professor of urban water management and global STEM professor at our School of Energy and Environment. He is a fellow of the Australian Academy of Technology and Engineering and a distinguished fellow of the International Water Association. He was named as one of the Engineers Australia's top 100 most influential engineers for 2015 and has been appointed as a member of the Order of Australia. That's why you can see his name with AM, means he is a member of the Order of Australia. He was an Australian Laureate Fellow awarded by the Australian Research Council. His research focuses on development of innovative solutions for urban water management through effective integration of fundamental science and applied engineering. His research areas include corrosion and odor management in sewers, greenhouse gas emissions from wastewater systems, resources recovery from wastewater, integrated urban water management, and digital water. He so far published over 500 peer-reviewed journal articles, including papers in famous journal Nature and Science, and attract over 46,000 citations with an H-index of over 118. He is one of the highly cited researchers identified the calorific He is also currently the editor of the famous journal Water Research X. He is the founder of 3 biotechnology companies. His research achievements and leadership have been recognized through many national and international awards, including the International Water Association Global Project Innovation Award. Without further ado, please join me to welcome Professor Yuan, please. So today he will talk about understanding and mitigation direct greenhouse gas emission from wastewater system to support net zero urban water management. Please.
Thank you. Can you hear me? Thank you, Kenny, for nice introduction and also for the opportunity to present to the audience here. I work on urban water management, which is not really on the marine environment, but urban water systems always upstream to the marine environment. Therefore, what we do to manage the urban water systems are relevant for marine environment management. My talk today is around net zero carbon neutrality for urban water management, or net zero urban water management. And this is actually a complex topic. And what I will focus on today is on the direct emissions from urban water systems. So I'll explain to you what I mean by direct emissions. Now, at the COP26, I think there's 26 water utilities from the United Kingdom, Australia, New Zealand, and serving 72 million people, and they pledged to achieve carbon neutrality by 2025, which 2 years away, to 2050. So really within a very short period of time, they aim to achieve carbon neutrality. And I believe more water utilities will follow. So there will be, there is a strong drive to achieve carbon neutrality for urban water management. So what does that mean? And a simple definition of carbon neutrality or carbon net zero is really the carbon emitted from your system is equal to the carbon sequestered plus offset. That's the equation. I'll explain each of the terms. In terms of carbon emission, there are three scopes there, 3 types of emissions. One is direct emission, which I will explain in the next slide. And another one is indirect. Scope 2 is indirect emission due to the consumption of power. So power stations are supported by fossil fuels, for example, and then by consuming power, and you emit carbon. So that's the scope 2. And then scope 3 is the emission due to the processes both upstream and downstream of urban water systems. Right? These are 3 scopes of emission. But when we talk about the carbon neutrality and what are included, include both scope 1 and scope 2. Scope 3 is not part of carbon neutrality, although some urban utilities, they aspire to include that as well, which that can be pretty massive, that can be massive emissions. So that's the carbon emitted. In terms of carbon sequestration, so the biological processes we have could sequester some of the CO2 from atmosphere or from other sources. For example, our nitrifying bacteria, for those who work on biological processes, nitrifiers, they convert CO2 into biomass. That process is CO2 assimilation. So that is sequestration, but that is very small, a tiny amount. So it's really negligible. But then if you deploy this algae-based technology, then you could potentially sequester quite a bit of CO2. And so that's important. And the third one there, I wrote as some biogas upgrading processes. That's a process we developed. I will share the ideas there with you towards the end of my presentation. Now, offset. This is very flexible. If in the urban water, in the wastewater treatment, for example, if we are able to recover some energy from wastewater, and part of that energy can be used for urban water management, and in that case, you reduce your scope 2 emission. But if you have excess power, if the amount of energy you can produce, is not directly used within your system, is actually exported to serve other communities, and that is an offset. So we have, if you export energy or power, you have offset. Or if you can spend money to purchase carbon credits, or you plant trees, and those will also reduce your carbon overall carbon balance, and so to help you to achieve carbon neutrality. Now, strategies to achieve carbon neutrality include, number one, we reduce direct emissions. We reduce scope 1. So these are gases you emit from your system. You reduce them, of course, and then you reduce your that helps you with the net zero. And then for scope 2, and there are a few things we can do. One is we reduce the energy consumption. If you reduce the amount of electricity you consume, of course, you reduce your indirect emission, indirect CO2 emission. Or you generate renewable energy power from your wastewater, for example, you generate, and then you reuse, and then you reduce your energy, you reduce the amount of energy you need to import, and then you reduce your indirect emission. And third is you can purchase renewable energy, like the power, solar power or wind power. If you use those for your wastewater management or wastewater management, and then that will also reduce your scope 2 because those power sources emit less amounts of CO2 in general. And the third one here is offset. So one, as I said before, if you produce energy, you export that energy to other communities, other clients, and then you're generating credit for yourself. And you're sequestering CO2, that is also helping you to offset. And you purchase carbon credits or you plant trees and so on. So that's all of those belong to the offset. So these are the ways to help you to achieve carbon neutrality. Now, this is with that background information, and my presentation today, I divide it into two parts. One, we focus on direct emission. What are they? And how do we, how much are we emitting from urban water systems? So I will focus on quantification, and our team has also been working on the fundamentals, the understanding and the modeling, etc. I will touch upon those aspects, but I won't be able to give details on the modeling and understanding, but I mainly focus on this question, how much are we emitting? And then I will get to part 2, which is on the mitigation. So part 1, we understand how much we are emitting. That's not enough. Does not really help you to reduce. So part 2, we focus on innovative technologies to reduce the energy consumption, to enhance energy recovery, to reduce direct emissions, and also to help to sequester CO2. If we can achieve those goals, we really physically reduce the carbon footprint of an urban water system. So that's the outline of my presentation. So part 1, direct emissions. So what greenhouse gases do we emit from urban water systems? So we really talk about 3 gases: nitrous oxide, N2O, methane, and carbon dioxide. So the first 2, I'm sure you all know already. They are strong greenhouse gases. Carbon dioxide, I need to make one clarification. In general, wastewater treatment processes, they emit a lot of CO2 because of the oxidation of organics into CO2 you emit. But majority of that is not regarded as greenhouse gas emissions because that CO2 is coming from biomass, which is short cycle, the carbon short cycle. CO2 assimilated by plants, we consume the plants, we emit CO2 back to the atmosphere, and plants will take it again. So that's a really a small cycle, short time cycle. So that is not considered as your contribution to greenhouse gas emissions. However, wastewater also has some carbon that is from fossil fuels, for example, and the detergents you're using, or so many things you're using in your household or in industry. And then if that carbon comes to the wastewater treatment plant, you oxidize that to CO2, and that is a direct emission. So I just want to make that clarification. Now, if you look at the carbon CO2 production, that's easy to understand. So we oxidize the organic carbon, we produce CO2. And if you look at methane, that's anaerobic process. I think most of people here should understand that the anaerobic biological conversions, organic carbon converted to methane. And that is the principle for methane formation. N2O production, I needed to explain a little bit. So as we know, in a I think for those who work on environment, biological reactions in environment or biological reactions in a wastewater treatment process, so you understand that a nitrogen cycle, the nitrogen cycle, biological nitrogen cycle is very important. So normally this is the important steps in biological nitrogen cycle. Ammonia oxides to nitrite by ammonium oxidizing bacteria by hydrosillamine, and then nitrite can be oxidized to nitrate by nitrite oxidizing bacteria. That's another step. And then denitrification from nitrate to nitrite to NO, N2O, and nitrogen gas. So that's the nitrification and the denitrification reactions, which are fundamental for biological wastewater treatment, because we needed to remove nitrogen from wastewater and using nitrification and denitrification. If you look at this, you can see N2O is sitting in the middle of the denitrification pathway. So it is a compulsory intermediate in denitrification. Therefore, a lot of N2O is produced by heterotrophic denitrification. Fortunately, that reaction happens in an anoxic tank, in a tank where there's no active aeration. No active aeration means no gas is leaving. Therefore, although N2O is produced, it is almost immediately converted to N2, not much emission. So that's a lucky aspect. But then if you look at the nitrification, ammonium oxidation, so this is the ammonium oxidation here. So here that's by AOB, ammonium oxidizing bacteria. They produce N2O as well. So this is what they do. They do nitrite reduction. So they don't do it for a known purpose, maybe for detoxification or for whatever reasons. They do nitrite reduction to NO and from NO to N2O. Unfortunately, they don't have the enzyme to continue to do the denitrification from N2O to nitrogen gas. Therefore, that is stopped there. Then that N2O is produced, and that N2O is produced aerobically. So that's because this reaction happens with the presence of oxygen, in the presence of oxygen, and oxygen is provided through aeration. So you have a gas going through and to provide oxygen, and that same gas will take nitrogen and N2O out. So whatever produced there, majority of that is emitted. So that's one process. Another one, and the green one, they called, that's also produced by AOB, ammonium oxidizing bacteria. And that pathway is called hydrosillamine oxidation pathway. So the red is AOB denitrification, the blue is heterotrophic denitrification, and the green is hydrosillamine oxidation pathway. And that is also produced aerobically, therefore it can also be stripped. So just like to give you some fundamentals so you understand better what I will be talking about. Okay. Now, I have covered what gases are emitted from an urban water system, and also explain how N2O is produced in an urban water system or wastewater system. Now, next question is where are these gases emitted? And what I have shown, what I'm showing here is a complete urban water system. We start from reservoirs where we store water, the catchment store the water for water production, and the catchment produce N2O and the methane. And then after water consumption, the wastewater goes through sewer networks where potentially we have methane and N2O. And then when that wastewater comes to the wastewater treatment plant, where the biological reactions will happen, and N2O, methane, and the fossil CO2 will be produced. And when the effluent, which still has some organics, going to the receiving water environment, that the river or estuaries, and N2O and methane can be emitted as well. And going to the bay, even in the bay and the marine environment, we also have N2O and methane. So basically they are produced everywhere. And my research team has actually worked on all these elements, but today I can't cover everything, but I'll show I will mainly focus on this environment, wastewater treatment, sewer networks. The rest I will touch upon briefly. Wastewater treatment plant first. So I guess the audience here in the room or online may not have a complete picture how wastewater is treated in a wastewater treatment plant. So I'd like to walk you through the processes involved in the wastewater treatment. So here we have wastewater coming to delivered to the treatment plant where we could potentially, not always, potentially have a primary settling tank where the suspended solids in wastewater, some of that suspended solids is separated and then diverted to this. I will come back to that point. And then the effluent, the settled effluent, primary effluent, is fed to a biological reactor or multiple biological reactors where biological reactions happen. And the biological reactions remove organic carbon and remove nitrogen. So here in this tank, that's where biological reactions happen. And then the biological reactions lead to the growth of bacteria. Here we have sludge, and here we have a secondary clarifier where the biomass is settled and the treated effluent is discharged after disinfection. And then here, majority of the biomass is returned to the reactor to retain the bacteria in the system to do the work for us, but some excess sludge will join the primary sludge and send to a thickener where we thicken the sludge, and then the thickened sludge is fed to an anaerobic digester. That's the energy recovery process. Anaerobically, we convert organic carbon in the sludge to biogas. That's a renewable energy. And then the digestate is dewatered through a dewatering process where we will have a digestion liquor, which is treated here or diverted back to the treatment process. And then here we have a sludge stream, and the sludge can be dried before being disposed for landfill or for agriculture application. So that's the biological process we have in a wastewater, typical wastewater treatment process. So where are the greenhouse gases emitted? So here, starting from the beginning, the primary settling tank, we could have a methane, but it's not formed there. It's formed in the sewer network, remaining in the wastewater dissolved, and which can be stripped here. And then that same methane can also be stripped in the aeration tank, and that's the methane emission. So these two are not really due to the biological reactions in the treatment process itself. It's actually formed in the sewer networks. And then in the biological nitrogen conversion happening in the biological reactor here, we can produce a significant amount of N2O, and which can be emitted. Then we can also have the fossil CO2. Now, in the anaerobic digester, and we form, of course, the purpose is to produce methane, produce biogas. And here, if you don't manage well, some of methane can go out, and that is emission. And then dewatering, in the digestate here, we have dissolved methane, some 20 milligram per liter. And then during the dewatering process, some of that can be emitted. And then also even in the digestion liquor, we also have some methane, and these two are also sources of methane. And then the sludge in the sludge drying lagoon, for example, N2O and methane can be formed. And so basically, all these processes can emit. So what I'm going to do today, I will mainly focus on these two, N2O and CO2 in the biological unit. These two, the methane emitted from primary tank, and here, which I will cover in the sewer part. I will come to the sewer part later. And then methane here from anaerobic digester, that's more a management issue, and I did not work on that. I think that can be improved through proper management. My team also worked on technologies to remove that methane from anaerobic digestion liquor, but I won't be able to cover that. And this, we also worked on this drying lagoon, but I won't have time to cover that either. So I will focus on N2O and CO2 emission from a wastewater treatment process. So that's the treatment process. Okay, this is a wastewater treatment process, and the first question we want to answer is N2O is emitted, but where in that treatment process and in the biological reactor, where is that emitted? So in the biological, I did not go into details. So in the biological reactor, we have anoxic zones where we provide no aeration, so no gas is going through the reactor, and aerobic process where we provide air to give oxygen to the process. So aerobic, anoxic. And then you can see what I'm trying to see is mainly from aerobic zones, less from aerobic zones. I like to bring attention to this slide I showed you before. Although we produce a lot of N2O through denitrification, but there's no active stripping. So therefore, very little N2O from denitrification is stripped. But for these two N2O green and red N2O sources, they happen in the aerobic zone. You have aeration gases going through and actively stripping that off. So therefore we have more N2O from the aerobic zones and then from anoxic zones. That's the first question and answered. And then by whom? Who are doing this? I think with my explanation, it's clear to you. The main contributor in terms of N2O production, heterotrophic bacteria, they produce most of the N2O, but it's not stripped. In terms of the N2O stripped, it's really, they're mainly produced by the ammonium oxidizing bacteria through those two pathways, the red and the green pathways. So that question was also answered. I probably won't show you the evidence, but just believe me. And then the next question, how much? How much are we emitting? And there are two different methods to quantify. And one method is to cover part of this aeration tank, biological reactor. We put some hose there, we collect the gas, and then we use online analyzer to analyze. And then we could also use some mathematics to estimate. So we don't need to go into details. Now, in some 15 years ago, my team started measuring quite a few wastewater treatment plants in Australia. I'd like to show you the results. But before I show you the results, I'd like to make one definition, the emission factor. So there are many different definitions of emission factors in literature. The one I'm using is emission factor is the percentage of nitrogen in the wastewater influent converted to N2O. If you have 100 kilograms of nitrogen coming to your treatment plant, you have 1 kilogram of N2O formed, and then the emission factor is 1%, right? So that should be simple. But then how high is high? Now, there's a rule of thumb here. So an emission factor of 0.5 defined above, if 0.5% of your nitrogen wastewater is emitted as N2O, and the greenhouse gas effect, the emission, is equivalent to, roughly speaking, to 20% of your overall carbon footprint, or add 20% to your carbon footprint. So that's very significant. 0.5% give you add substantially to your emission. Now, ready to show you some of the results. So in that round, measurement campaign, that was the second round of our measurement campaign. Literally right now, the team at UQ is doing the third round. So you can see the 7 plants there, and then these are emission factors we determined. So the lowest we found was a 0.17, which is really good, very low. But highest we found was 1.9, so wide range. The median level is about 1%. Remember, I said 0.5% would add 20% to your carbon footprint. 1% will add 40%. So that is not negligible. It's a fair bit. So that's our results. And then before our measurement campaign, there was another campaign in the US, and this is the results reported. That was in 2010, so 13 years ago. And the summary is the emission factor 0.01 negligible to 1.8%. So the range is very similar to what we measured. The median level is 0.4. I have reasons to believe that may be a little bit underestimated. So because of the early stage of measurement, the methodology was still being developed. So that's 0.4% may be a underestimate. Now, these are some of the results summarized in a recent literature review, recent 4 years ago. And so this summarized different measurement campaigns, and they found a range between 0.01 to 2%. So very similar to what we found. Average is about 0.9%. So you see, fairly consistent. And I think this data mainly based on the European measurements. Okay, now, how much? So this is what the IPCC, for those who do not know, IPCC is the International Panel, Intergovernmental Panel on Climate Change. IPCC, they proposed accounting guidelines for different units. So you can see what they proposed is 1.6%. So what they did was they plotted the N2O emissions against total nitrogen loading, and then they draw a regression line, and the slope of that line is 1.6%. So they came to the conclusion 1.6% should be the emission factor. And ironically, they got it wrong. They got errors in their calculations. So this is David DeHaas is one of my colleagues, and he actually investigated all the data used and corrected all the errors, and he found 1.1%. So 1.1%. This is actually close to the median level in our measurement or in the European measurement. In the European measurement. So 1.1% or around 1% is roughly the emission factor. I think this is better than the 2019 guidelines. I hope IPCC will take on board. Okay, this is useful. So once we know the emission factor, so that give us an idea how much we are emitting, but it does not really help us to reduce, right? So if we use 1% for accounting, making no effort to reduce it, and that does not help us reduce the carbon emission. Therefore, I believe that's not adequate. We should really further improve that emission factor estimation based on performance. Okay, so this is also done by David DeHaas and Liu Ye, both my colleagues at different stages of their career. And what they did was, and also along with some European researchers, what they did was emission factor vertical axis. They plotted emission factor against TN, total nitrogen removal performance. So for nitrogen removal, the higher the better. You wanted to have a high removal because that's wastewater treatment plant wants to remove nitrogen as a pollutant. But then so the blue dots are the European data, and the orange are the Australian data. And you can see the two lines, regression lines. They go down with the removal rate. That means the better the nitrogen removal performance and the lower the emission, which is really great. I put a thumb up here because this is with some luck, because that means the goal of reducing emissions aligns very well with the goal of nitrogen removal, not the other way around. So I believe at least in the future, when we talk about emission factors, we should link emission factors with the performance. So we encourage utilities to achieve high TN removal and the emission factor. Now, that's the N2O. I like to give one slide on CO2 emissions from a treatment plant, not because the results are and the emission is significant, because method is quite interesting. Some of you may use the method in your own studies. So what we did was we made use of the fact that the biomass, the plant biomass, the C13, C14 levels in plant biomass are different from C13, C14 levels from fossil carbon. So if you have different C13, C14 signatures in the normal renewable carbon and in the fossil carbon, we can use that to separate using some of the machines, I guess, our key laboratory has. And we can determine how much fossil carbon we have here in different stages of the treatment. And so for those who are interested in this technique, you can check our paper. That's a 2013 publication. And conclusion is 1 to 7% of the normal of the wastewater, of the greenhouse gas emissions from a wastewater treatment plant can come from the fossil CO2. That's a general conclusion. And we now I'm coming to methane, another source, methane emissions from sewer network. In the IPCC guidelines 2006, they said no, no emissions. So and then we in which year was it? 2008, we published our paper. This is the first paper to show they were wrong, and there are significant methane emissions from sewer networks. That's from our research. Unfortunately, they did not really correct that issue even in 2019 guidelines, but they did recognize that that's something to be considered in the future. So our team continued to work on methane emissions from sewer networks. And so I can probably skip all the details in the interest of time. And really, the conclusion, basic conclusion is there is significant emissions. That's most of the time it cannot be neglected. Now, how significant it can be? Based on the amount we measured, we estimated the typical CO2 equivalent per megaliter of wastewater compared with the normal emissions from a treatment plant, we came to the conclusion somewhere between 3 to 40%, meaning from negligible in some cases to very significant 40% you can't ignore anymore. So that's the conclusion we had. But the issue, this is a figure shows a sewer network. The issue with the methane emission from sewer networks is extremely hard to quantify. Not like a wastewater treatment plant you can measure. Sewer network spreads across the city and with a lot of openings, manholes, pumping stations, you can't really easily measure those. So we came up with this approach of model-based estimation. But in the end, I'll show you the key results. So we have come up with accounting guidelines. We are hoping that IPCC can adopt eventually. So for gravity sewers that are driven by gravity, this is the equation we propose. So very simple, Q is the flow rate, D is the diameter of the pipe, S is the slope of the pipe. So once we know those and we know temperature, and we can estimate methane emissions. For rising mains or pressurized mains, we get a different equations. So we're hoping the research work is going to influence the policy, influence how this IPCC is going to recommend in the future. So this is an example to show how we use the equations to estimate methane emissions from a sewer network in DC, Washington, DC, in collaboration with some of the colleagues in the US. Now, two slides on the methane and N2O emissions from waterways, the bays, the rivers, estuaries. I thought this may be of interest to you. Unfortunately, I don't have strong conclusions. We did work on those areas for quite some time. So that's a bay, that's Brisbane in Australia. So this is a big bay there. We had this our sampling locations along the river. This is the river. This is the bay. So you can see a lot of work there. And we did to generate this is reservoirs, water storage dams, the supplying the drinking water in Australia. So we did produce a lot of results for each of those systems we measured. Unfortunately, the conclusions are not extremely strong because it's very difficult to draw general conclusions. So here are the conclusions. Large variations between systems. Each system is different. There are different levels of emissions in different systems, and large spatial and temporal variability. So vary between in the same system, varies between locations and vary between different time of the year and a different time of the day. We observed all those variability. And then another one, this may be relevant, is the methane dominate in reservoirs upstream, N2O emission more dominated in the bays and estuaries, rivers. And then the other conclusion I can draw is in Australia at least, and it's very hard to separate the contributions of urban wastewater to those emissions. And because the water treatment is quite advanced in Australia, we could not really separate the contributions of the urban water system to methane and N2O emissions from the receiving water environment. So part one summary, I think I used too much time already. Part one summary is I think over the years, we have generated a lot of understanding of methane and N2O emissions, and we show mitigation is possible. But I'd like to draw your attention to the last conclusion I draw there. Unlikely to achieve net zero with the current technologies. That's an important conclusion. I'd like to explain what I mean by that. So here in this diagram, we show direct emissions. The blue bar is direct emissions. The orange bar shows the electricity consumption, and the green bar shows the energy recovery. So therefore it's negative CO2 emission. And then the black bar is the blue plus orange and then minus green. That's the green black bar. If we want to have net zero or carbon neutrality, and that black bar should be at a zero level. So with the current technology, we conclude it is very difficult. So then we need innovative technologies to reduce the carbon footprint. I already said what we need to do. We have multiple goals we want to achieve, but the key issue there is, are these goals consistent? So when you achieve one goal, are you actually deteriorate another performance? So if they're not consistent, the good news is they actually reasonably consistent. That's what I like to show you. Okay, so this without going into details, this is a full-scale mitigation effort. We made a we designed an online control system for aeration control, and with that good aeration control, we achieved 20% energy savings and 35% reduction in N2O emissions. So I said we could potentially have conflicting goals. So if you want to reduce energy consumption, you could potentially increase N2O, vice versa. And fortunately, this is not the case. The goal of reducing energy consumption is consistent or is compatible with the goal of reducing N2O emissions. So that's, with some luck, I think that's beautiful. That's really nice. So but in this particular case, we managed to reduce both direct emissions and energy consumption, which is really good. Now, as I said, with the current technology, it's going to be very difficult to achieve net zero. The reason for that is this anaerobic digestion for energy recovery is an add-on feature to a treatment process. So historically, we treated wastewater using this technology, this technology, and then afterwards we said we give afterthought. Oh, we should also recover some energy, so we give this digester. And the amount of energy we can recover here is relatively small. And therefore, in order to achieve net zero, we actually need to do something fundamental to the design of a wastewater treatment process. And so I'd like to highlight the importance of carbon, organic carbon for the nitrogen removal. So I already said nitrogen removal, ammonia to nitrite, nitrite to nitrate, and nitrate denitrification, nitrate back to nitrite and to nitrogen gas. So in this whole process, for denitrification, we need organic carbon. And in order to have that organic carbon, we actually need to give most of organic carbon through this process rather than to the anaerobic digester. So that's a fundamental difficulty in achieving high level of energy recovery. In fact, in most of the treatment plants in Australia, we don't have a primary settling tank anymore in order to completely remove that separation. So we have this, all carbon is fed to the biological reactor to support denitrification. With that, we actually increase the carbon, the energy consumption here. So the goals do not really add up there. But now, commonly in the wastewater treatment area, the commonly accepted configuration for the next generation is we actually need to enhance the upfront carbon separation by, for example, by use the HRAS process. So we include the HRAS process, we separate as much carbon as possible from the wastewater and divert it to the anaerobic digester for bioenergy recovery. And then the carbon deficient wastewater we feed to the air, to this biological treatment unit to remove nitrogen. The problem is when we don't have much carbon there anymore, we can't use conventional nitrification, denitrification anymore because denitrification requires carbon. And then, so we do achieve the goal of energy recovery, much enhanced energy recovery. So we need to deal with that nitrogen removal. So here we use partial nitridation animals. And for those who have heard, so we oxidize 50% of ammonia in the wastewater to nitrite. Then we use the nitrite formed to oxidize the remaining 50% of ammonia, and then we produce nitrogen gas. So you can see we remove nitrogen without carbon, and we allow the carbon, by doing so, we allow the carbon to be diverted to the digester for bioenergy recovery. So all beautiful. And by doing that, we also reduce energy consumption here. So we reduce energy consumption by 50–60%. So if you look at this, we recover more energy using carbon separation, and then we consume less energy. So these two goals we can achieve simultaneously, which is beautiful. I'll show you some of the results, literature, and this is the process, the system without the separation. You can see we have primary settling tank. Then this is the energy consumption, this is the energy recovery. So this plant, actually, we got a very good energy recovery, but that's only 50% of your energy consumption. That's with the primary settling tank, what is achieved. But now, if we look at we use HRAS. If we include this HRAS for carbon separation, you can see we can remove 60 to 80% of COD, of organic carbon in wastewater for energy recovery. That's really good. And you can really recover a fair bit of energy from wastewater, bioenergy from wastewater. And then with that, what we don't need to worry about the details. You can see in terms of energy recovery, we have more energy recovery in these three cases, and energy consumption is reduced a lot. If you compare the white bar with the black bar, the white bar is now taller than the black bar, meaning now the system is energy positive. You can produce more energy than what you consume, which is beautiful. Now, the problem, so these two goals are achieved. So we achieve energy recovery and we achieve energy consumption reduction. So both of these goals are achieved simultaneously. The problem is really there's an incompatibility here. N2O emission largely increased. So here we got the process, the partial nitration NMOX process to remove nitrogen, and which experimental studies showed it produces a lot of N2O, 3.7%. Remember, 1% is about the norm for the current technology. This is 3.7%, and this is one case study, but it's not unique. And if you look into literature, the average emission factor about 4%, from 1% to 4%. And then we can look at what this means. So you have seen this before. This is black. We want to bring it back to zero. So therefore we want to change the energy recovery and energy consumption balance. Now we have the green energy recovery larger than the yellow, and then it means energy positive. But the problem now is the emission factor, the blue bar goes from here to here, 4 times higher. And then the black bar, in comparison to the normal, the current technology actually increased. We're not achieving, we're traveling against our will to reduce the carbon footprint. So we needed to bring the blue bar down. That's what my team focused on in the last 5 years, to bring that down. And okay, so we perform an analysis and we generate a hypothesis of what the reasons for the high N2O emission factors were. And based on the hypothesis, we designed this process. So this is what we came up with. So this carbon separation, instead of having one biological reactors to do the PNA, we incorporate another one, which is we use a partial denitrification NMOX, and here is a partial nitration NMOX. So this no aeration in the yellow tank and aeration in the red tank. And we have biofilms incorporated in both processes. And then we have another feature, which I have no time to explain today. And performance in terms of we did 5 years, and the design, the pilot plant, the construction, struggling, and this is the final year we got there. Nitrogen removal, so you can see the red here is influent nitrogen varies a lot because that's real wastewater. That's at a treatment plant, wastewater treatment plant. Effluent below 10, which is the target. Effluent composition, so really this is a purple ammonia, and then the rest is almost zero. And a summary of the effluent quality, very good, meaning our system was able to achieve nitrogen removal. That was important. But very, very importantly, look at the N2O. So N2O emission factor, 0.18 from 4, right? 4% down to 0.18. And that was really beautiful, some of the details. Okay, now look at this carbon balance here. Look at the carbon footprint. So this is the current technologies. This is the PNA. We wanted to bring that blue bar down, which we managed. If you add these 3 together, and this is the black bar we got. So now with this technology, we can achieve carbon neutrality, zero carbon. So that was a successful story. Okay, final. This is I'm coming to the end of my presentation. I don't want to use too much time. And this is the final example I'd like to show you. This one, I try to show you CO2 sequestration. So the first, okay, well, I have shown you this diagram before. So we said we have a lot of direct emissions. We want to reduce those direct emissions, which we did. We want to reduce energy consumption for this, right? This example is different. We wanted to sequester carbon, CO2. So in the stream we target is this one, the biogas. We know biogas roughly, you have a 60% methane, 40% CO2, and that is a significant amount of CO2. Normally that CO2 is not a problem because that majority of that comes from biomass, renewable carbon. So that's not really matter. Nevertheless, if you can sequester that, you get a credit because carbon is carbon. If you can lock it up, and then you can really, by locking up that carbon, CO2, you reduce your carbon footprint. So we developed a technology to lock up that carbon. I'll show you how that worked. And so we used an electrical chemical process, and with, the work is just published in Nature Communications earlier this year, just a few weeks ago. Electrochemical cell, we use iron plate, iron as electrode. So we give a little bit of a voltage there. We oxidize Fe to Fe2 plus, ferrous. Okay, at the cathode, we split the water into hydrogen and hydroxide. So the simple electrochemical reaction, I mean, well known, is not our invention. So what we proposed was this: biogas produced in a wastewater treatment plant containing methane, CO2, and a few traces, other gases. Then we pass that through. Because we have hydroxide produced, so this solution is alkali. And when CO2 goes in, and the CO2 is locked up there. And then CO2 will bind with that Fe2 plus. So this is the reaction. CO2 locked in, producing ferrous carbonate. I'll show you the overall reaction. Frozen. Oh, it works. Oh, I'm not. It's okay. Yeah. And I hope this works. So this is the red is the overall reaction. So we basically, in the whole process, we use the iron, which can be recycled iron from car engines, and then we lock up CO2, forming Fe carbonate plus some hydrogen. And then what we achieve, you see in the off gas, we got the biogas upgrading. So the CO2 is removed. We mainly have methane and hydrogen, and this is a good gas source. You can compress that gas. You can use that car fuel and a few other things. So you can inject into the gas network to the home cooking, and so the value of the biogas is elevated by that process. So that's good. And at the bottom, we form Fe carbonate slurry, and the carbon is locked in Fe CO3, and that's not leaving the system anymore. It's there. So it's permanently removed from the gas phase and get into the liquid and possibly into the solid phase at some point. But if we just stop there, the innovation was not strong. What we have done was we actually use that Fe carbonate for urban wastewater management. So coming to this, I'd like to show you this. So this is the urban wastewater system, sewer network and wastewater treatment plant. In the urban wastewater management, Fe, so ferric chloride, often used in the wastewater process. So added at a multiple points. And for example, in the sewer networks and the beginning, and then that Fe would react with the sulfide forming FeS. You deal with the odor issue. Sulfide cannot go out anymore. And so that is happening in Australia, very common. And here we do, DSD is using that as well. So that's a very important technology for sewer odor management and corrosion management. Then can also be added to the wastewater treatment process where we remove phosphate. So phosphate and ferrous, and can form FeP minerals. And then you remove P, phosphorus, which is also a nutrient you want to remove. And then can also be added to the digester. If you add it to digester, you control sulfide in biogas. So a lot of applications already, multiple points in urban wastewater system where you add iron salts in the form of ferrous or ferric chloride. And then And additional benefits does include the settability of the sludge, which is very, very important, means a lot of dollars, enhancing the workability of the sludge, also a lot of dollars involved there, benefit. And one issue with the current technology of ferrous or ferric chloride is lower the pH, and that's not very desirable. Lowers the pH, lowers alkalinity, not desirable. And then that's the current situation. Now we are able to produce a ferrous carbonate using biogas, and this is the situation. So we use our electrochemical cell and we produce a ferric carbonate. So we've upgraded the biogas, which is nice. We lock out CO2 at the sink, is also nice. Now we propose to use the ferrous carbonate to replace whatever used now for the urban wastewater management. And we did all the tests, so no time, no need to go into details. So we demonstrated the Fe carbonate, which is what we produce. And what you buy, you can buy Fe carbonate in the market. It does not work. Only our freshly produced Fe carbonate can readily replace the ferrous carbonate, ferrous chloride for sulfide removal in sewer networks, P removal, treatment plant, and hydrogen sulfide removal from biogas. And very importantly, and we addressed one issue with the current technology, we actually elevate the pH. Elevating pH is always a good thing in wastewater management. So here, another good example. Now I'm coming to the conclusions really. I think energy neutral and energy positive or even energy positive sewage treatment operations is possible. And carbon neutral sewage treatment, or carbon neutral, yes, that's energy. Carbon neutral is also, neutrality is also possible. Key factor is we need to recover as much energy as possible using carbon separation, and we needed to deploy innovative technologies for nitrogen removal. And over the years, I mean, so many people participated in the research I presented to you, and I can't sort of show all individual pictures. I'll show you the picture of our group. This is research center I led before I joined CTU. We had about 100 people. Okay, finally, I'd like to, as Kenny introduced, I'm a chief editor of Water Research X, so welcome to submit. And normally there's a fee involved, but for good papers, you can approach me, I might give you a fee waiver. Yeah, thank you very much.
So once again, thank you, Professor Yuan, for wonderful, inspiring talk. Now I open the floor or also for the online attendants to ask questions or comment or give comments. Maybe to warm up, may I ask a couple of questions first? I wonder this the emission factor for N2O, whether it will be affected by temperature. So in tropical area, will we expect higher level than temperate region?
A very good question. Yes, it is affected by temperature. I can't speak about marine environment. I think many people here would be concerned about N2O emissions from a marine environment. But for wastewater treatment, generally speaking, the higher the temperature is, the lower the emission, which is really good for Hong Kong because of the climate here. We have a high temperature. The reason for that is ammonium oxidizing bacteria. If you give them in summer, when you have a higher temperature, they are very active, and so they have a lot of capacity. And the loading, if the loading remains more or less the same in winter and in summer, that means in summer they have extra capacity, right? So what we found was the less you push them, the better they work for us. Oh. So meaning in winter, you have a higher emission because winter, their capacity is constrained, right? And they have lower capacity, but they still have to do the same job. Nice. So therefore they emit more. Summer, they have a lot of capacity. You still load them with the same job. Then they can do it very, relaxed manner. And then they don't emit as much.
Very interesting. I also saw your figure about the relationship between the N2O emission percentage against the x-axis, the total nitrogen removal. Yeah. I see there a huge difference between Australia and European emission.
Yeah.
So Australia seems doing better.
Australia is worse in that.
Worse, yeah, in the
worse,
graph, yeah, on
above,
that side,
right?
yeah, yeah.
And that's against what I just said. Australia normally should have a higher temperature. There should be a lower emission, but there are many other factors that would contribute to that emission. I can't really tell conclusively why in Australia we have observed a higher emission factor, but hypothetically, it could be due to the shorter sludge age we apply, because normally, if you keep the same sludge age, theoretically, a higher temperature will give you lower emission. However, when you have a higher temperature, you have a higher temperature. Therefore, when you design and operate a treatment process, you already considered that factor. And that means you don't have to give 20 days retention time of biomass. And you can give 15 days or maybe even 12 days. In that case, you are reducing that capacity. By reducing the retention time, you are already pushing the bacteria because your biomass stays there shorter. Therefore, their capacity is limited by the time they can stay in the system. And then if that's the case, I'm saying this hypothetical. I haven't really verified the SRTs, etc. That's hypothetically, that could be a reason why, although you have a higher temperature, you still have a higher emission factor. So there are so many factors affecting the emissions.
I see. So in Hong Kong now, because for sardine sewage treatment plant, because they try to control the smell, then they cover all the tank, like
in the cave,
the preliminary sedimentation tank and also the activated sludge tank. Then I wonder if we cover, can we harvest those N2O if we make it as an enclosure?
Yes, so you can harvest, but the N2O concentration is too low. N2O concentration, if you have, let's say, 50 ppm, 50 ppm or 100 ppm of N2O in your off gas, that's very, very high. And the emission factor is very, very high. You cannot afford it. But then the 50 ppm of N2O, you can't really do anything with it.
Okay, so no benefit.
Value, no value to do it. Okay. But that said, there are some engineers or researchers or practitioners proposed this so-called can-do process in the US and Stanford University. They try to deliberately produce N2O from wastewater sources and then harvest that N2O as rocket fuel, and which when N2O can be a good fuel, but the issue is how much you can harvest is probably not that much.
Yeah, interesting idea. Now I leave it to the floor, our young scientists, to ask you questions. So yes, please, gentlemen. The microphone.
Sorry, regarding the difference between Europe and Australia, do you think the original nitrogen content in the water could be a difference maker there?
Not really. Domestic wastewater, the sewage we talk about, it's the Europeans and our Australians eat similar diet, right? We eat beef, we eat meat, we eat some other type of biomass. And then that's really the protein after degradation and converted to ammonia. I think the source is very similar. But the ammonium concentration may be different. The nitrogen concentration in wastewater may be different. In some of the European cities, many of European cities, because they're old, you have combined sewers, meaning the stormwater and the wastewater, they're collected using the same network, and then there could be very good dilutions of ammonia, and that may have an effect on the whole biological conversions. Australia, normally we use a separate sewer, and separate sewer means ammonia concentration could be higher, but not always. I mean, even the sanitary sewers can be, it's prone to stormwater intrusion. So we have observed even with the separate sewers, the flow rate of wastewater during wet weather days can be 4 times of the normal wastewater flow. So that means a lot of stormwater actually gets into our separate sewer as well. So it's a lot of uncertainties there. But the source of ammonia should be the same. It's all come from our urine. 80% of the ammonia in wastewater from urine.
Okay, Dr. Yip, please. Okay, Dr. Yip.
Yeah, thank you for the nice talk. Because our group works on the CO2 reduction, so maybe I will ask the electrochemistry part
Yeah.
for the recent work. My first question will be, what will be the concentrations in the for the CO2 in the emitted gas mixtures?
In the raw biogas,
Yes,
40%.
40%.
Normally, so normally in biogas, depending on your processes, is somewhere between 30 to 50%.
30 to
The average
50.
level about 40%.
Yeah, and that will be useful because we can directly convert the CO2 maybe into some methanes or some other
Of course.
fuels. And the other is about the subsequent use of the iron carbonates. If you want to use the iron carbonates to capture the sulfur, then you need to again to release the CO2 back to the environment because you substitute the carbonates with the sulfur. Am I correct? In the second step, you need to use the carbonates, iron carbonates, to react with the sulfide.
Sulfide in sewer network. Yeah.
Then you again emit
Yeah. I
CO2.
know what you mean. What do you mean? So when you add a ferrous carbonate to sewer network, and the ferrous carbonate will break up, and the
Yes.
ferrous will react with sulfide, forming
Yeah.
FES, and the carbonate is released to your sewage as carbonate, not as CO2,
and
not as CO2. And
Yeah.
then you may argue, and that's part of that will one day leave the water to the air. So that particular molecule may actually leave the water phase, getting into the gas phase. But generally, by having carbonate injected into your water is able to assimilate more CO2 from atmosphere than it emits from atmosphere to the atmosphere. So the overall balance is that CO2 is always locked into not that particular molecule. Generally speaking, the amount of CO2 we add to wastewater using Fe carbonate, they are locked in. Not only that, when you discharge that treated water to rivers, oceans, they can actually take a little bit of CO2 from atmosphere into the water phase. So the sink is actually a little bit bigger than what I showed.
Yeah, and then the last question would be like, if we look at the loop of the ions, eventually we convert the iron to the iron carbonates and eventually go to the iron sulfide. Then what do we do with the sulfide, iron sulfide?
Iron sulfide, when the iron sulfide gets into the wastewater treatment plant, because you have aerobic condition, and that FES will be oxidized. And then that sulfide part will become sulfate, which you have plenty of sulfate in water, so that's no problem, that's discharged. And that Fe part becomes will bind with the phosphate, will help you to remove phosphate. I did not really have time to explain the beautiful flow-on effects of that. Iron is an interesting element because it has got Fe2 plus, the two valent is 2, Fe2 plus, Fe3 plus, and then aerobically, Fe2 will become Fe3, and anaerobically, Fe3 will become Fe2. This iron cycle, we are using that iron cycle in the wastewater system with the beautiful results, but I don't have time to share with you today. You can read our papers. So you asked a very good question.
We have an online guest to ask a question. He is Professor Jiang Sanru from HKUST. He said, Professor Yuan, a quick talk. In one test, iron reacts electrochemically with CO2 to form the ferric carbonate slurry. When FeCO3 is used later, will CO2 be released? Quite similar to
the same question.
Professor Jiang Sanru, would you like to elaborate? You can speed up.
Hello. So we're good friends.
Professor Jiang, are you online?
Hello.
Yes, please. Yes, please.
You want to show up your face? It's all right. I know how you look.
Yes, please elaborate your question.
Yeah. So I think you just passed my question to Professor Yuan. So he may already answered my question.
Okay.
Yeah, I think I've answered your question there. Maybe just very briefly, if you talk about the one individual CO2 molecule, and that may be emitted, but overall, if you look at the overall CO2 balance, no of the carbon in the ferrous carbonate would leave the water phase.
Okay. Do you have any follow-up questions, Xiangyu?
And no, at this moment, that's really a very insightful, very informative talk. Thank you, Professor Yuan.
Thank you.
Thank you.
Thank you, Professor Liang.
I have another question. Since the government now we have problem with food waste in Hong Kong, we produce more than 3,000 tons of food waste, but we only can deal with a couple hundreds of them. So now they put some of the food waste into the digester for co-digestion.
Yeah.
What is the implication in terms of the methane and N2O release?
That should be, my understanding is there should be no N2O implication. It's really methane producing more methane, which is a good thing. So co-digestion, if your digester has extra capacity to cope with the higher organic loading rate, I think co-digestion is a good thing. And then, of course, then digested after dewatering, you got a digestion layer that need to be treated. There's nitrogen there, and then the treatment of nitrogen-rich stream will release some N2O. So in that way, maybe some implications to N2O, but we have technologies or processes to deal with that nitrogen stream. So.
Because now they're also doing a trial, you know what, food waste, they separate to dump in different bins. But in US or other country, they have a shredder in your sink. Yeah. When you put washing your dish and your vegetable, those parts you don't want you put in the sink, it's shred for you and become a small particles and then go to sewage.
Yeah.
Then Hong Kong also thinking about this. Would you think this is good way or will have a burden on the system?
Well, I can't talk about this with a great level of authority. I did look into this. I know some friends, some colleagues in Hong Kong, I think were working on this, probably from UST. I have concerns there, depending on your sewer design, and the particles, they always settle. So you need a minimum velocity for the particles to move, right? And if the velocity is here high enough, and then to be able to suspend the particles, then obviously there's no issue. It's a good thing. But if in certain sections of the sewer pipes, the velocity is not high enough, and therefore the particles settle there, then you will have two issues. One is sediments will build up, and potentially you can have a sewer blockage, more risks, higher risk of a sewer blockage. Theoretically, that can happen. Another one is when you have formed sediments, organics forming sediments, then the guarantee you methane will form. And then the methane formation in sewer networks, there's no mitigation. You have to allow that to form, allow that to leave. And so you could, in terms of greenhouse gas emissions, that could be
worsen.
So that's just based. I never did any experimental work myself, but based on what I know, what happens in sewer networks, I have those two concerns.
Yeah, they only try in some buildings now. Just have a test.
Yeah, it's used in Australia as well. My house, we got this grinder there, and we rarely use it. All depending on the sewer network condition, it can have detrimental effects, but it may not necessarily be the case depending on your design.
I see. So, any question? If over there, please, Henry.
Yeah, Professor Yuan, thank you very much for this nice talk. So I have a bit general question. So municipal wastewater is also a significant carrier of various micropollutants, and some of them are like we concerned, like emergent POPs. So they also undergo the entire chemical and the biological process in the wastewater treatment plants. So my question is, do you think the presence of these micropollutants or their participants in the chemical or biological process are beneficial or play a counter role in means of carbon neutrality? If they are beneficial, how can we utilize it? Or if they're a counterpart, how can we attenuate this effect?
Yeah, I think that all the micropollutants, they're all different, right? So their effect on the biological processes will be different. And I can see potential negative effects if some of the micropollutants interfere with some of the biological reactions, like AOB metabolism or denatrification. If they inhibit particular enzymes, and then they could lead to more higher N2O accumulation, and that could give you more N2O emissions. So this is a theoretical possibility. In terms of positive effects, I can't really imagine, readily imagine any positive effects. But because micropollutants are all low concentration, so their presence does not really contribute that much to the metabolism of others, unless they have interference with some of the enzymes. So I can't really imagine positive effects there, but who knows? But there are depending on the accuracy of your machines. And so there are tens, hundreds of thousands of those micropollutants and all different types. Each of them can have a different effect. So there's probably no definite answer to your question. In fact, some of in Germany, in Switzerland, and they have changed their processes to remove those micropollutants and advanced oxidation, etc. Very costly, very costly to remove those micropollutants. From that perspective, the costly means you have to give a lot of energy, right? If you, by removing those micropollutants, you invest more energy into it, and then there is a direct effect on the carbon emission because you consume more energy, more CO2. So there's a multifaceted sort of thing we have to consider. So there's no definite answer there.
Thank you very much.
So any question from students? Maybe I ask one for you. So how can be a good scientist, and how can we do better as a student, a PhD student?
As a PhD student, okay. Kenny, we all professors, we know students need to graduate. They need to publish papers, need to graduate. And so I accept that pressure. That aside, I think you need to work with your supervisors to identify a real research question to solve. It's very important. Rather than very short-sighted and saying, this is cheap, this is a quick thing I can work on, I can publish a paper. If I started today and 2 months later I can get a paper, and those paper-driven research is definitely not something I recommend. You will have short-term gains. You can graduate and maybe that helps you, and more publications will help you find a job, but you won't go too far. And a good scientist, detached from students, and a good scientist, you should always identify the real problems to solve, and then solve them in an innovative way. So you communicate with your clients or industry partners, you ask them what problems you have, and then among the problems, some of those can be readily answered by consultants. They have knowledge there, and it's just a matter of knowing the knowledge and apply the knowledge, and that should not be your research focus. You should focus on those challenging questions without current knowledge. And the clients know they need new knowledge to be developed in order to have those addressed, and that will be the best questions for you to focus on. Now, once you identify those questions, some of those questions, yes, you develop new knowledge and find a solution, but will not give you publication. Can give you publications, but not highly cited papers, because that topic itself is a relatively cold one. There's not too many people working on those, and there are also some other research questions you develop knowledge, you can generate papers, and you attract a lot of citations. So there you may have a choice. Not necessarily I'm advising you to focus on those the hot topics. Sometimes you can have more contributions by focusing on cold topics. And talking about myself, Kenny introduced at the beginning. Yes, I do have a lot of citations, some 40-something, 40, you said 46,000 citations, a lot of citations. But that's probably the citations are because of half of my publications, and the other half have less, right? So not every paper was cited at the same level, but the papers attracted less citations. That's do not necessarily mean they are poorer quality papers. The whole citation business is more about which area is hotter than other areas. It's all about how many people are working on that topic, right? If more people working on that topic, although your paper may not be the best in your publication list, but will attract the highest citations simply because more people are working on that topic. And some of the very good research work I did not attract so many publications. However, those type of work has attracted a lot of funding. So that's not in my CV. In Australia, my 25 years working as a professor in Australia attracted 50 million Australian dollars. Wow. And that's 250 million Hong Kong dollars research funding. And not necessarily all my highly cited papers were attracting the funding. This is really, relatively speaking, the low citation papers with low citations probably. Yes. Yeah.
So don't work just for publication. Work for good question,
impact, right?
And solve the problem. Yeah.
Yeah.
And I can feel the passion of Professor Yuan. He has a passion to love science, to find the answer. This is very important.
In the same time, as I said, I do understand and appreciate the pressure that everyone is under. As a senior academic, I'm less under pressure because one more or 1,000 more citations or 1,000 less citations do not matter that much to me anymore. Or one more paper actually does not really matter that much anymore. But for you, it is important. So I do understand and appreciate that. But considering that, I hope you can also consider some other goals in your research work, not just simple papers.
Yeah, very good advice. Please join me once again. Thank you, Professor Yuan.
Thank you.
So as a tokens of thanks, I will present a small gift to him.
Thank you. Coffee cup. Excellent. Thank you very much. Thank you. So just a second.
Maybe John.